Hey guys, just gonna wait a couple of minutes to see if anyone else is joining the waiting room. We've got about 12 people on and another 4. We've got people coming. So this session is on alcohols, alkanes, and alkenes. So quite interesting. I think there's a couple of mechanisms in here. I think we've got maybe electrophilic substitution as the core mechanism to do. But yeah, hope it proves helpful. Just wait another couple of seconds. Just wait until everyone gets it. Right, let's get going. Yeah, it is put on the YouTube, by the way. Okay. So basically starting with the properties and reactivity of alkanes. So what are alkanes first? Alkanes are a group of compounds which have the general formula CnH2n plus 2. So for every carbon you have 2 times the number of hydrogens times 2 plus 2. And alkanes have saturated hydrocarbons. So saturated only single bonds. Butane, and then you've got basically all these other types which are unsaturated, but alkanes remain saturated. Hydrocarbons are any compound made up of only carbon and hydrogen, so alkanes are hydrocarbons. And a cycloalkane is a special type of alkane. The reason is because it's still saturated, but has the general formula CnH2n because it's a cyclical structure. It's quite cool. Remembering alkane molecules have 4 bonded pairs, no lone pairs. So they have a tetrahedral shape around carbon atoms, with a 109.5 degree bond angle because of only sigma bonds present. And alkanes show structural isomerism. So an alkane with the same molecular formula can have slightly different structural formulas due to the permissibility for straight chained, branched, and cyclic molecules. So you have different types. Can you tell me which type of structural isomerism this is? It's chain isomerism, yeah, because it's to do with the chains, side chains. Yeah, perfect. Alkanes are non-polar. So remembering that in terms of your bond intermolecular forces, we only have weak van der Waals forces, which means that longer alkanes, which have more electrons, will also have more higher melting and boiling points because they have more van der Waals forces. And so this is crucial in the principle of fractional distillation, because you have molecules that separate and the alkanes will separate. So remember, longer carbon chains have larger surface areas and have more contact points, and they also have more van der Waals interactions, so they have greater melting and boiling points. Also, straight chains can be stacked closely together and have a large surface area for interactions. So straight chains form more van der Waals forces and have higher melting and boiling points. Okay. Complete versus incomplete combustion. So complete produces CO2 and water, whereas incomplete, it produces carbon monoxide, carbon, which is soot, and also still water. So remember, water is the priority one. We produce water first. That is all balanced out. It's the carbon that tends to be potentially a little bit controversial with whether we produce it or not. So remember, these are just quickly listing through some of the different pollutants. Carbon monoxide, toxic, binds to hemoglobin more strongly than oxygen, so it reduces the ability for the blood to carry oxygen. Soot or particulates cause respiratory problems, including asthma, as well as global dimming. Smog produces photochemical smog, which basically contributes to global warming. Nitrous oxide makes acid rain with nitric acid, and as well as sulfur dioxide, and that's deadly. Sulfur dioxide, again, will react with rainwater to produce sulfuric acid, and so causes acid rain. So some specs require a bit of a knowledge of catalytic converters and slurry, so how we can remove toxins. So catalytic converters basically take your toxic products, they perform reactions with a variety of transition metals in a large surface area ceramic cone, and then they produce non-toxic products like carbon dioxide, nitrogen, and water, which is then released back into the environment. And we also have a slurry, so slurry containing calcium oxide and calcium carbonate, which produces calcium sulfate, and then that's removed to get rid of the sulfur dioxide. Oh, okay. So this is the first kind of step that reaction we need to talk about. So I'm going to quickly just kind of describe this quite summary based. So you have 3 steps. So step 1 is initiation. And we know this from basically the principle to this is initiation, you are producing free radicals. So start without FRs and end with 2 FRs. Yeah. Then you have so initiation is the initial step, propagation, which are the middle steps, where a free radical reacts with a non-free radical to produce, and this is over 2 steps. And then you have termination, which is free radical, I'm just going to call them FRs for now. FR plus FR gives you a non-free radical compound. Yeah. So that's kind of how you identify how each step kind of will look. I'm going to talk you through an example, and then we'll do a couple together just to get you guys practice on this, because this is a really important reaction that you need to know. So let's do CH4 plus Br. Yeah, Br2. So the first step, initiation, is you take your Br2 and you split it. So you form Br, and I'm just gonna put the dots at the bottom because, you know, they're not very kind of easy to do just up. The next step is the first propagation step. So we're now reacting a free radical with a non-free radical. So we know that the only other non-free radical thing we have is that. And that produces a CH3 free radical plus HBr, which is our secondary product in this reaction. The third step, the second propagation step, again, we go back and we react that non-free radical with the non-free radical Br2. Oh, sorry, mistake here. That's CH3. With the non-free radical Br2 to produce our final compound that we want to produce, CH3Br, plus the Br radical. So as you know, we know this for a fact that the radicals are acting as catalysts in this process. And we know that makes sense because they're used up in the original reaction, produced at the end of the second reaction. So they do act as catalysts. And then the last step can be whatever you want it to be. You can react to Br free radicals to reproduce Br2. You can do CH3 plus CH3 to produce C2H6. Or you can do Br plus CH3 to produce a secondary CH3Br. You can make that whatever you want it to be. You can do any combination of the radicals that you've ever produced, just react them together, and that's your termination. Does that make sense, everyone? Yeah, perfect. So we're now going to do a couple of practice ones, maybe like 5 practice ones, giving us 5 minutes of just good practice on this, because I think that would be very useful. Basically, I want you in your own sort of notes, I'm sure you're taking notes on this, just to write down, I'm not going to check it or anything, but just to write down kind of what you're thinking. C2H6 plus Cl2. Let's do, okay, I'm going to bully you a little bit and make the second one a little bit hard. It's going to be CFCl3 plus O3. Now, what can anyone tell me what reaction that is? Anyone? That is a reaction you used to need to know in specifics in the old spec. You don't need to know in specifics in the new spec. It's the depletion of ozone. So it's how the ozone layer is basically gotten rid of, almost. And let's do one more. And I've given you a kind one to end with. So if you want to I'm going to give you up till 30 paths just to write down everything that you're thinking. Does the O3 turn into, yeah, sorry, I didn't show that. I didn't explain that properly. Yeah, the O3 will turn into O and O2 and O. Yeah. And the CFCl2 usually gets regenerated. It's because the radicals will always react with each other, basically. So yeah, it's possible. Can two free radicals any two? Yeah, exactly. Right, perfect. That's hopefully given you guys enough time to have a little bit of practice of that free radical substitution stuff. Yeah, so we know this is the process. We're doing this. Remember that because it produces a mixture of products, and oh, can I go through number 2? Yes, I can. Let me see. Okay, so CFCl3 or plus O3. So the first thing we do is we form a free radical. Now, this first step is based on your knowledge of bond enthalpies. Really, it is based on your it's based on your knowledge of bond enthalpies and realizing that the CF bond is significantly weaker than any other bonds, right? So what happens? Sorry, no, CCl is weaker. So CFCl3 turns into radical CFCl2 plus a Cl radical. Yeah. So we've started with that. That's initiation. The second step is the Cl radical reacts with O3 to produce ClO plus O2. And this ClO remains a radical because technically it's not doing it with the transfer of oxygen. And then ClO radical reacts again with O3 to form a Cl radical plus O2 plus 2O2. So overall equation is actually very simple. It's just 2O3 becomes 3O2. And that's it. That's the overall equation. Because this is a intermediate and this is a radical. So basically the CFCl3 ends up being fully regenerated almost. So it's basically just a catalyst, which is why this is a serious problem. Because if the CFCl3 can just be regenerated, then even the tiniest amount can have a devastating impact because it's never going to leave. It never depletes itself. It just continues depleting the ozone layer, which is why we need to which is why the use of CFCl3s were banned in aerosols and fridges in the early 2000s because everyone realized that they were actually really, really bad for you, like really, really bad for the environment. All right, yeah. So remember, there are loads and loads of unwanted products that can form, and this is because, first of all, you can have a chain reaction, again, because of the idea that this is the catalyst, and because free radical substitution can happen at different points along the oh wow. Hey, can you hear me? Still on Zoom. Oh, okay. So I've been signed out of the Zoom, but I've not been disconnected from the call. That's a bit weird. Okay, so I am still here, right? Right. Yeah, cool. That's fine. So you can still see my screen. Everything's still pretty normal, like working fine. Okay, fine, cool. All right, obtaining alkanes. This should be fairly self-explanatory in the sense that it is literally fractional distillation and cracking. So stuff that you've probably done many, many times. So petroleum is a finite fossil fuel obtained by drilling and is made up of basically dead plankton over millions and millions of years. It's really, really compressed. It's tightened. There's loads and loads of carbon life form in there. And basically then the bones just obviously degrade. It's basically tightened plankton. It's very difficult. You can't produce that like outside of a natural environment. And fractional distillation is the process by which, because remember, this crude oil or petroleum is a mixture of loads and loads of different hydrocarbons. And we need to split them so we know that exactly what goes into the hydrocarbons that we're using. And this is based on a different boiling point in a fractionating column. So what you do is you heat petroleum till it becomes a gas. You then put the gas in this fractionating column. And the gases will condense in this column at different points. Basically, smaller molecules travel further up, larger molecules condense at a higher temperature, and this is because of their van der Waals forces. And then you take them out and you use them. Cracking is the process of turning a really long chain alkane into short chain alkane plus an alkene. And you can do this by basically passing over, it's basically two processes. You can either do this by heating it to a very, very high temperature for a very short amount of time and triggering thermal decomp. Or you can do it by using catalytic cracking, which is basically a lower temperature, low pressure, and a metal catalyst. So you pass this gas over the metal and it produces alkanes as well as some aromatic hydrocarbons. Aromatics, anything that contains a benzene ring. So slightly different processes to it. Okay, let's do alkenes now. And then we'll do the one mechanism that you need to learn. Don't know if we'll have time to get onto alcohols, because I do want to leave some time for questions, but we can do alkenes and we should have time to do the mechanism that I want to do, which is addition, electrophilic addition, as well as the polymerization process that you need to know. So alkenes, group of compounds with the general formula CnH2n that are unsaturated. So this is the crucial difference, is that basically these compounds consist of a carbon-carbon double bond, which makes them unsaturated. So not anything with the general formula of CnH2n is considered an alkene, because as we know, cycloalkanes also have CnH2n, but it has to be unsaturated. Alkenes, yes, they do. Yeah, they do have the same. The carbon-carbon double bond basically is consisted of two, a sigma bond, which is just a shared pair of electrons between two carbons, as well as a pi bond above and below. So let me explain how pi bonds form quickly. Don't know if you need to know that. Kind of. Not in a lot of detail, but you remember pi orbitals, right? Pi orbitals are, or p orbitals, sorry, are like the dumbbell-shaped clouds. So you remember that it basically kind of if you looked at it from a kind of, as you know, it's like sigma pi delta, and then there's way more just in between. Sorry. Yeah, so p orbitals lie above and below the carbon ring, above and below the carbon chain. And basically, when these electron clouds are pushed near each other, there's an overlapping of these electron clouds, leading to two basically very, very electron dispersed. So unlike a sigma bond, which is very, very electron dense, a pi bond is actually dispersed over a large area because it's about electron clouds molding. And so in comparison, the pi bond is stronger or weaker? Let's take a guess. It's more dispersed, so there's less electron density. So it's a pi bond. Yeah, a pi bond in its direct sense is weaker than a sigma bond. But the thing that a pi bond has is that it's never by itself. It's always in conjunction with a sigma bond, and therefore it increases the overall strength of that area. Yeah, so a pi bond by itself has a much lower bond enthalpy. But remember, bond enthalpy, as I'm sure you all know, is not dependent on a specific bond within a molecule. It's dependent on the entire bond as a whole. So actually, this carbon-carbon double bond has a huge bond enthalpy because it's not only the pi bond, but it's the pi bond plus the sigma bond. So that's a crucial thing that I'm sure you all know, is that bond enthalpy isn't to do with one part of the total bond, it's to do with the whole bond as an entirety. But actually, you can find that on tables, because you can see that a carbon-carbon single bond is X. No, let me see if I can find bond enthalpy values. Okay. So this has got, this has got double bonds in it as well. So you can see that a carbon-carbon single bond is 347. Yeah, but a carbon-carbon double bond is 614. Now, if the pi bond was stronger than the sigma bond, we would expect it to be at least double plus more, right? Because it's the addition of an extra bond, and if that extra bond is stronger, it's going to take it to double plus more. So we would expect the bond enthalpy of this carbon-carbon double bond to be at minimum 695. But the fact that it's 614 indicates that the carbon-carbon double bond, the bit that makes the double bond, is actually weaker than the bit that makes the single bond by itself. But because it's an entirety, it ends up feeling stronger. Does that make sense? Cool. Carrying on. Let me just carry on. So anyway, we've got this, but this leads to a really important feature of alkenes, which is limited rotation around this carbon-carbon double bond. Basically, what happens is the carbon-carbon double bond can't rotate, and that means that we can have EZ isomerism. Electrophiles, another key definition, is an electron pair acceptor. That's what you need to know about it. And they're attracted to areas of high electron density because they like electrons. And you can work that out basically from breaking down the words. So electro, meaning negatively charged electrons. Philes, meaning liking, like thermophiles, like heated conditions. And yeah, there are other examples of that. So examples of electrophiles normally are positively charged ions or polar molecules. And this is because in a polar molecule, let's go for HBr as an example, electrons are pushed very closely to one end. So there is an area of delta negativity and delta positivity. Yeah. Right, carrying on. So a carbocation is any ion with a positively charged carbon atom. Now this is the reaction. So this is basically electrophiles are always positive. The bit that's electrophilic will be positive. Electrophiles as an entirety might not be. And in the example that we showed, HBr is a polar molecule, but it doesn't have an overall charge on it. It's not an ion. But because of that electronegativity difference, because the electrons are pulled so far towards the bromine, the bit on the hydrogen is really not that significant. Sorry, the bit on the hydrogen is going to be positive there. Okay, we'll talk about that. We'll talk about that mechanism later. Bromine water, orange to colorless, is the test for any unsaturation. Doesn't necessarily have to be a test for alkenes. It is just a test for unsaturation as a general. It's literally just a test for, and basically it's because of the mechanism. The mechanism is the same as the mechanism that you would kind of be anticipating. So basically this 4-step mechanism. So the first step is electrons. So there's the polarity. Basically, that means electrons from the double bond are attracted to this area of positive charge, which breaks off this area of negative charge. And that creates a carbocation. There's a lone pair of electrons on the bromine, which is attracted to the carbocation, forming the saturated molecule. Yeah, do you guys know this mechanism? I'm sure you've done this many, many times. Any questions about it? Take a second for you just to. Nope, no questions. That's fine. And this is the same principle to basically for this reaction. For HBr, it's the same thing. How the pi bonds are not strong enough to induce a dipole? It's to do with what they are. So remember, pi bonds, the question is, why aren't sigma bonds strong enough to induce a dipole? And this is because they are very localized, right? Sigma bond's electron density is incredibly localized. And we know that a pi bond, the electron density is quite diffuse. It's quite spread out. And this is really good to induce a dipole, because what it means is it can attract areas of positivity. Because if you think about it, it has a wider kind of area of influence almost. Yeah, so there is more attraction towards it. Whereas a sigma bond is very, very localized, and it's just between the small area, so there isn't as much. Does that make sense? Yes, no? It's to do more with area, not strength. Even which is an important principle that you'll get onto. I don't know how many of you are in A2. Oh, I'll repeat that in a sec. But I don't know how many of you are in A2, but this is an essential principle you'll get onto in benzene, because benzene can induce a dipole because the electron ring is very well spread out. It can't induce a huge dipole, which is why you often need an acid catalyst when you're doing electrophilic substitution in benzene. But it can still induce a dipole. And we know that phenol is stronger at inducing a dipole because even though the ring is still very diffuse, there are more electrons added to it. So as I was saying, basically, it's to do with the fact that the electrons are quite well spread out, so they have a greater area of influence or a greater area of attractability. Basically, they're so spread out that anything that comes in their pathway is kind of taken up by them. If you imagine a pi bond kind of like a tornado, like a huge tornado, anything that's in their vicinity is just taken up. Benzene to nitrobenzene, electrophilic. Yes, it is. Benzene. Benzene can induce a weak dipole. It can still induce a dipole because otherwise you wouldn't end up having let me think of the reaction you wouldn't end up having. No, because the catalyst no, benzene can still induce a weak dipole. It can't induce a strong one. Yeah, you do need a carrier, but the carrier, it's still, so benzene can still induce a dipole. It's more complex than that. So benzene, I think, can still induce a dipole, which is then used by the carrier to react. And then that's again then used by benzene. So there's a lot more to it. It's quite complicated. But it was what I remember when I did A-level, that was what my teacher was talking about. So benzene induces a dipole, and the carrier then kind of helps it. Does benzene only do electrophilic? No, there are other reactions benzene does, but yeah, I think I'm not exactly certain which ones they can do though. I know there are definitely more reactions though. I think electrophilic sub is the main one you need to know. And yeah, benzene to nitrobenzene is catalyst in the nitration of benzene. That should be, yeah, it's tin. Isn't it tin and concentrated HCl? Yeah, tin and concentrated. Yeah, nitric acid or concentrated acid. No, sorry, nitration of benzene is HNO3 and sulfuric acid. Tin is hydrogenation of that. So that's to converting that. So nitration is to go to nitrobenzene, and then to get to the amine form of that, then you need tin. So different reactions. But nitration is nitric acid and sulfuric acid. Okay, we've got on to slightly different questions here. But yeah, this is the same principle. The last thing I want to talk about, I don't think we'll get onto addition reactions. We need to talk about this. So primary carbocation is more stable, is less stable than a secondary carbocation, which is less stable than a tertiary carbocation. And that's Markovnikov's rule, which is that the major product will have the hydrogen in the hydrogen halide bond to the carbon atom already bonded to the highest number of hydrogens. So basically, hydrogen will always go to the tertiary before it'll go to the secondary, before it'll go to the primary. Does that make sense? Yeah, that's Markovnikov's rule. And it's because electron donating groups have a positive inductive effect on the positively charged carbon atom, so that more alkyl groups, the more alkyl groups attracted to it, the lower its charge density. That's complicated language for it, but yeah. So exactly the same principle. You induce that dipole, you basically then electrons go to the one with the most. Sorry, what? So can you tell me if this is the major or the minor product? This reaction, does it produce a major or minor product? Is it the major? Why? Yeah. Again, yeah, it produces, the hydrogen is bonded to the one with the least hydrogens. Okay, so electrophilic addition, again, it's in the same reaction process. Basically, here though, you have to do it. So you do it with sulfuric acid, and then you break the sulfuric acid as a catalyst. So that's basically the process of hydration with sulfuric acid. Basically, it just breaks that up again. Okay, have a go at this one, reaction mechanism. So propene and sulfuric acid. and we'll show you the answer after this. Cool. And so those are the answers to this one. So you form, basically break the double bond, hydrogen goes to 1, and then the SO2. SO3OH goes to the other one. Remember, you can react it with hydrogen in the presence of nickel or platinum to produce an alkane. You can react it with steam in the presence of an acid catalyst, such as phosphoric acid, to produce alcohols. You can oxidize with potassium manganate, and that produces basically a change. There's a color change in that, and you can go from an alkane, and that's oxidation, alkane to an aldehyde, aldehyde to a carboxylic acid. So that's also possible. So I know you might have been taught that it's only possible with an alcohol. You can also do that with an alkane if you convert it basically to an R group, then to its aldehyde carboxylic acid ketone. So you can do the same pathway, just slightly differently. Cool. Any questions? We've basically covered a little bit of alkanes. We've done electrophilic, we've done free radical today, which are the big two mechanisms kind of thing. They're probably the biggest two mechanisms you also need for your AS exams, generally for most of you. Sorry, I can't share the PowerPoints with you. They're copyrighted. Any other questions? No other questions? Cool. I will see you guys on Sunday, hopefully, for the exam, for the biology session. I think this week is second last week, so I think it's on classification and stuff. Not exactly sure though. Anyway, adios. Bye.